This movie discusses the implicit treatment of the 1D heat transfer equation. I've written down a discretization for the heat transfer equation with the time derivative and the second order space derivative. I use time levels n+1 and n. Note that I have used the temperature at time level n+1 for the second order spatial derivative, which means I have an implicit treatment of this equation. Let me introduce the diffusion number. It's equal to delta t times alpha over delta x squared, with alpha, the diffusivity, equal to k over rho times c. Diffusion number is a dimensionless number. It should remind you of the Fourier number that was treated during the heat transfer classes. The delta t times alpha is a distance squared, so the square root of delta t times alpha is a distance, and it's a measure for the distance over which heat is transferred in time delta t. Having introduced this number d, we can simplify our first discretization by multiplying the equation at both sides by delta t over rho times c. Then I get the following expression containing the diffusion number d, the familiar coefficients 1, minus 2, 1 for the second order derivative, and I get a modified source term, which now also contains the factor at delta t over rho times c. How do you continue when you want to solve this implicit time stepping problem? Bring all new stuff to the left, all old stuff to the right. So all terms containing the temperature at n+1 have to go to the left, and the temperature at time level n has to go to the right. And if you have done this, you get the following expression, which contains the temperature at time level n+1 at the left hand side for points I-1, I and I+1, with constant coefficients, minus d, 1 plus 2d minus d, and the right hand side, which is equal to the temperature at the old time level plus a term related to the source term. This last expression should remind you of the equation that we got for the stationary heat transfer. We can write down this equation for all points I, which means we have a system of equations, system of linear equations. And since each equation contains the point I and its neighbors, it's a system of coupled equations, coupled linear equations, which means that we can solve it in very much the same way as we did for the stationary problem. To stress the fact that we have an equation very similar to the stationary case, I've also written down the equation in the ABC form, introducing the coefficients a, b, and c for the points at I-1 left neighbor, I central point, and I+1 right neighbor. A is equal to minus d, b is equal to 1 plus d, 2d, and c is equal to minus d. And the vector RHS for the right hand side, it's equal to the temperature at the old time level plus a term related to the source term. So we also have a system of linear equations. Let me compare the coefficients for the implicit case with the coefficients for the stationary case. For the stationary case, remember the A coefficient is k over delta x squared, B coefficient is minus 2k over delta x squared, and C coefficient is k over delta x squared. For the instationary case, A coefficient is minus delta t alpha over delta x squared, so it's negative as opposed to positive for the stationary case, and it contains this delta t. C coefficient similar, minus delta t alpha over delta x squared as opposed to k over delta x squared for the stationary case. And for the B coefficient, we have 1 plus 2 times delta t alpha over delta x squared positive as opposed to minus 2 k over delta x squared for the stationary case where it is negative. Also compare the right hand side. For the stationary case, it contains minus the source term in point I. For the instationary case, it contains the temperature at the old time level plus a term related to the source term. Remember, we are going to solve this equation iteratively, and for the stationary case, we told you that the matrix for the stationary case is nice. Why was it nice? Because the absolute value of the B coefficient is bigger than or equal to the sum of the absolute values of the A and the C coefficient. And it's a fact that the bigger the B coefficient with respect to the other coefficients, the better it is for iteration. Now note the instationary coefficients, minus delta t alpha over delta x squared for coefficient A and for coefficient C. For the B coefficient, we have 2 times delta t alpha over delta x squared. So we already have a situation similar to that for the stationary case. But additionally, we have this number plus 1. So the matrix for the instationary case is even better suited for iteration than the matrix for the stationary case. This concludes this movie about implicit treatment of the 1D heat transfer equation.